Good morning. Today's lab, we are going to be looking at electric energy. We've been talking in class about electric energy, electricity, how much energy is there based on the voltage, based on how much current there is. And so this lab is going to give us a chance to go in and set up a circuit and measure the current, measure the voltage, calculate how much power there is, at what rate is electric energy going into our circuit. And then what we're going to do is we're going to use that to heat up some water. So we've looked at thermodynamics. You guys have been through thermodynamics. And so what we're going to do is we're going to take a calorimeter with some water inside. We're going to take a heating element. So the power supply, the electrical power supply that we have, is going to be connected to a heating element. The heating element is going to have some amount of resistance to it. And based on what the current is and the resistance, the voltages, we can figure out the rate at which electrical energy is going into the heating element. Now the heating element is going to be submerged down inside the water. So to a good approximation, I think we're okay imagining that all the electric energy going into that heating element is going to go into the water. So the water is going to heat up. Now the water is inside a calorimeter. So the idea, and here's our calorimeter right here. So the idea there is, well, let's take a look and see. Let's remind ourselves what the calorimeter looks like. I kind of got everything set up here, so I'm going to try to pay attention here and make sure it's turned off. So first of all, I got a thermometer set up for the calorimeter, and I'm going to pull out the heating element. So I don't know if you can see this. We'll do a close. We'll do some closer shots of the heating element. But there it is. Here is the heating element, and there's a couple of connections that we can make, a couple of posts that we can connect the wires to. And then, if you remember, there's an inner calorimeter cup. And the assumption is that the calorimeter has been designed so that if we heat something up inside here, this is thermally insulated. So that calorimeter cup and the water that's inside here, that's thermally insulated from the environment. So there's this outer cup, which we're going to imagine doesn't heat up. And then there is this insulating ring. And the inner cup fits into that. So there's the heating element. Now, I've tried to color code the wires here, and again, we'll get a closer look at this in a minute. But what I've done is, I've got a power supply here, and I was looking at what voltages we could work from. It turns out the power supply has a 6.3 volts AC connection. That seems about right. It's not too high voltage that we're worried about the safety here, but it's high enough voltage that it should heat the water up in a reasonable amount of time. So I've plugged into that. So here's a couple wires plugging into the power supply. And again, this is rated at 6.3 volts, and it's AC, it's alternating current. So if you remember, when we're thinking about, well, here's the circuit here too, I guess. Here's the power supply. Here is the wire headed over to the calorimeter. Here's another wire headed over to the calorimeter. Now, along the way, we want to be able to measure the current, and we're going to want to be able to measure the voltage. Because when we're looking at electric power, the electric power is going to be V times I. Ooh, I guess resistance gets left out today. So the power here is it's going to be V times I. Now, if it's alternating current, what we found out in chapter 25 maybe, is that the power, the average power for an AC circuit is given by the RMS voltage times the RMS current. So we've been through this idea of AC voltages. And AC voltages, the voltages is varying, and it switches direction back and forth, and then so does the current. So the current, because of the voltage differences, the current is being driven back and forth, and Well, we've had examples of that, so if you want to review some of that, go back and look at some of the examples that we've presented in class. So that's going to be the power that we want to work from. Now, that says that we need a voltmeter and we need an ammeter to do these measurements. Now, I'm using what we call multimeters. They can do it all. So what I can do with the multimeter, this one I'm going to use as my voltage measuring device. So I'm going to turn this to voltage, and then I'm going to select AC. So I want to make sure that it understands that it's measuring an AC voltage, and that the voltage is on, and that we're set to voltage. Now, the connections here are, one of the plugs goes into what we call the common, and then the other plug goes into where it says voltage. So this is really important. We've talked about this a bit in class too, that voltmeters have a lot of resistance in them because they're measuring voltage. So what they're trying to do, they don't want a lot of current going through. They want to reduce the current down as much as they can. They just want to measure what the voltage is between two locations in a circuit. Now, for that, what we've done is we've taken the voltmeter and I've placed it with these wires over here as close to the calorimeter posts as I could. So again, here's the calorimeter, here are these posts that we've connected the power to, and I've placed the voltmeter right at the location of the post. We want to get as close as we can to that heating element to get a reliable reading on the voltage. Now, we don't want the voltmeter to disrupt the circuit. So voltmeters are built with a lot of resistance, and that means the current, when the current is coming through these wires, it's not going to, very little of it will go through the voltmeter. You know, almost all, essentially all of the current, almost all, is going to go through this resistor. So that's the idea here. Now the ammeters are kind of they're different. So for the ammeter actually has to determine how much current is flowing through a particular location in the circuit. So the ammeter's got to be built right in to the circuit. Now this is AC, but let's imagine the current, we turn on the power supply, and we've got current moving all the way through this circuit. So I'm going to outline this and say, this is the main circuit that we have set up. It goes down through the heating element, and then there's a couple connections to the power supply. So that's the main circuit, is power supply is sending energy to the heating element. Okay, and that's where the current is going to be running. So the ammeter's got to be part of that. The ammeter's got to be built right in, and that's why we place the ammeter the way we have. Now what that means is, let's take a look at the setup. So for the setup, I used red wires. I drew these in black. I used red wires. That didn't work. That was green. I used red wires. Does that look red now? To connect to the heating element. Okay. And then what I've done, so here they are. And then here's the ammeter here along the way. Now I got to be careful with the ammeter. I'm going to place one wire at the common. Now over here I'm going to place the other one where it says reading current or reading amps. And so I have to make sure when I set this, when I turn it on, that I turn it to amps and that I select it for AC. Now why is that important? Well, ammeters don't have much resistance within them. Ammeters are meant not to disrupt the circuit. But for an ammeter that's built right into the circuit, not disrupting it means it doesn't have very much resistance. So whereas with a voltmeter, if I accidentally wire the voltmeter the wrong way, it's got a lot of resistance. It's not going to have a huge amount of current go through and possibly burn out the voltmeter. But the ammeter is very susceptible. So if I set up the circuit in the wrong way, where there's too much current going through the ammeter, it'll burn out the ammeter. Okay, so we're careful placing the voltmeter, but we're extra careful setting the values on the ammeter. So please be careful with those. We burn out several ammeters every year, unfortunately, and unfortunately I'm probably the one that burns out most of those when I'm not paying attention. Anyway, that's what the circuit looks like. Now, we went through the electric power. Let's take a look at the thermal power. What's happening down inside the heating element? Well, this thermal energy, Q, that's not electric charge, right? This is back to thermodynamics. So for today's lab, Q is back to being heat. And that's going to be related to a temperature increase. So we've got the calorimeter cup, and we've got water inside. So I'm going to include the effect of the water heating up, MW, CW times delta T. And then I'm also going to include the effect of the calorimeter. Mass of the calorimeter times the specific heat of the calorimeter. Now if you remember, the objective here was to measure that guy right there. No, sorry, this one over here. The specific heat of the water. So let's see where it ends up when we go through this derivation. Now what I'm going to do is I'm going to scale this down into some infinitesimals. So I'm going to say every time a little bit of Q comes in, a little bit of heat, it's going to raise the temperature just a little bit. I can take that formula, divide both sides by dt, just dividing by the same thing on both sides. Now what I have on the left side is I have the thermal power. I have dq dt. Well, that's the thermal power. That's the rate at which heat is showing up in the water. Okay? And what we can do is we can take the electric power, the rate at which electric energy is being sent into the heating element, and set that equal to the rate at which heat is going into the water. Right? Energy conservation. And so dq dt is going to be equal to mass of the water, specific heat of the water. That's the heat going into the water. Here is the heat going into the calorimeter cup. That's going to get multiplied by dt. Now the big T on top is what? That's temperature. And the little t down below is time. So what is dt? When we solve this algebraically, what we said is we're after this value right here. We want to get the specific heat of water, and the formulas that we've set up here, if I carry out the algebra, that's the formula we're going to plug into. So this is all derivation over here, and this is the formula we're actually going to plug into. Well, the RMS voltage and the RMS current, those are coming off the multimeters, right? So I'm going to be able to read those. And then the mass of the calorimeter cup and the specific heat. Now I set that on a scale. I got a scale right down here. And the calorimeter cup came in at 67.3 grams. All right. So that's going to be the same every run. I can measure that once and then we're done. So again, that's the mass. It's not including the water, but just of the aluminum cup is the 67.3 grams. Now, let's see, the specific heat for aluminum, I looked this up, it said the table said 0.900 joules per gram per Kelvin. So I'm always a little nervous writing this. Maybe I'll write it this way just so we don't confuse order of operations. So it's joules per gram per Kelvin. Okay, so those numbers are known. So those are going to go in the very same values each time. You know what it comes down to? Ooh, mass of the water. How are we going to measure the mass of the water? Well, we measured the mass of the calorimeter cup by itself. And then I filled this, you know, it's got like, I don't know, 150, 200 grams of water in there. Something like that. A couple hundred grams of water maybe. Now what I can do is I can reset it onto the scale and then subtract off the calorimeter cup. And that'll tell me what the mass of water is that I'm working with. All right, so that's down inside. So we went through the whole circuit. Ooh, I gotta get the, okay, this turns out to be important too. I got a thermometer. I have to make sure the thermometer's actually down in the water. So I I measured this earlier. I'll have to re-gauge this and make sure I've got it right before I start taking data. But I want the thermometer, so it's a ways down in the water. The heating element is a good ways down, fortunately. And so when I put the water in, I want to leave some space at the top so the thermometer can fit inside. But I don't want the thermometer right up against the heating element. The heating element could be at a bit of a higher temperature. So a couple of issues that we have to pay attention to here. We are going to have to keep the water swirling. We're going to have to keep the water moving so that we have some convection going on. Otherwise, what's going to happen is the water near the heating element is going to heat up. But if we just wait for conduction to take place, the outer regions of the water won't be at the same temperature. So I wanted to create some convection by swirling this around and make sure. So we've got to slowly be stirring or just, rocking it back and forth. Swirling around too helps set up currents so that as the water goes in circles, the thermal energy is being spread uniformly. We want the entire sample of water to heat up together at the same temperature at each step of the way. All right, so this is the formula, or this one, that we're going to be plugging into. dTdt is the rate at which the temperature is going up, right? I'm putting thermal energy in, temperature's going to be going up, and we want to find out what the rate is of that temperature increase. So let's get a data table set up. Now we're going to do 3 runs. The runs are going to be 15 or 20 minutes. I know this takes some time. This is kind of as exciting as watching water heat up, because that's what it is. We're watching water heat up. And so, but we're going to take 15 or 20 minutes. We don't want to dump the heat in too fast. I mean, we want it not to take all afternoon or all morning to get through this. But at the same time, we don't want to run the heat in there too quickly. We want to be able to keep the temperature more or less uniform. So, and we want to observe the heating effect. So what we're going to do is, we've selected voltages that seem to work pretty well. During a time of 15 to 20 minutes, my guess is that the temperature will go up 15 or 20 Celsius, typically, with the setups that we have. So that's going to be enough. If we watch, a 15 or 20 Celsius increase, that will be pretty significant. That's something that's easily measured. So we'll go in and we'll measure, let's say every minute. So you do have to pay attention. So every time we get to a multiple, 1 minute, and then at 2 minutes, and then at 3 minutes, we want to take a look at that thermometer. And during the meantime, you want to make sure that you're swirling this, not too vigorously. Sometimes, students open up the calorimeter and find out the water is splashed all over inside, which is not good either. So very gentle swirling. But we want to get the temperature, we want to follow the temperature as it goes up. So I made up some numbers here. Let's say we start off at 21.3 Celsius. That's what the thermometer reads. Now I got a couple of backup thermometers because I'm always interested in seeing if the thermometers agree with each other. So we can check and see. Sometimes they don't. Sometimes they have a little different, as much as maybe a ½ degree or so difference between our thermometers, which is a little unsettling, I guess. Anyway, they're supposed to be good thermometers. So here's the temperature as a function of time. So here's our time axis. And as you can see, this is our graph, or these are the graphs for the week. So we'll do 3 of these data tables, and then we'll do 3 of these graphs. Now you can put all 3 of these runs onto the same graph if you want to. If you do that, make sure that the 3 runs are very carefully color-coded somehow so we can tell one run from the next. And then what we want to do with those data is we want to come up with a linear fit line. if the energy is going in at a linear rate, turns out the power supplies are pretty stable, so once we take those voltage and current measurements, and we'll check it from time to time, the voltages and currents tend to stay pretty constant through the runs. So we want to do a linear fit line, and then we want to find out the slope, because the slope it's dt dt. That's what we want. So you might say, well, why are we doing a graph and collecting so much data? Why don't we just heat it up for 15 minutes and then come back and see what temperature it is? Well, we want to see if the increase in temperature is actually linear. There's a couple things going on here. First of all, the calorimeters are not ideal. There is going to be some thermal energy transfer through the calorimeter. And what's going to happen is we get up to 25, 30, 35, 40 Celsius. Often what will happen is we'll see an effect where at first we see that the temperature is going up linearly, but then it kind of drops off sometimes. Okay? And so what's going to happen is, once you get up to 35, 40 Celsius, the water's getting up to a pretty good temperature, and we're going to end up losing some of that thermal energy. Now, if that happens in the data, what we probably want to do is not include any data where it looks like the temperature's kind of topping out, where it's hitting some kind of it's asymptotically approaching some value, or even just rounded a bit. So if this begins to rise at less and less of a slope, we probably want to take the early data, because I'm guessing usually what we find is that the early data is really linear, and then as we get up to higher and higher temperatures, it's a little less linear. So anyway, watch for that. So here are the data tables. I'll go in and we'll go in and we'll get some measurements on these, and then plot your data and decide, do the linear fit, decide which data you want to include, and then as always, I would say plot all the data in any case. And if you do see a bit of a leveling off here, then do the fit line with the data that you feel like is reliable, and do the measurements from that. And then, as always, explain why you're not including some of the data points. Okay? Don't just throw out data points because they don't agree with what you were hoping to get. You need some kind of a reason that other people can look at, so they can use their critical thinking skills and decide whether or not that was a justifiable thing to do. All right, so here are the graphs. Here's the circuit. I think we've got everything set up. You guys have questions? Let me know if you do. The last part of the lab, so I said that the objective was to measure the specific heat of water. Now that means that we're going to have some kind of, oh no, I don't have a results table. Where should I put it? I'll put it right here. Okay, what's the results table going to look like? We've been doing enough of these labs now. So what we can do is we can take measured values. Maybe you want to do each run. Measured specific heat of water, accepted specific heat of water, and percent difference. Sorry, I kind of squeezed that in. But that's a standard results table for us. So we want to be able to get values for each one of the runs. What's the specific heat that we measured on run 1? What did we get on run 2? What did we get on run 3? Report those. Report some kind of an average. So always do some kind of an overall average of all your results for the day. And then we'll compare those measured values with the accepted value, and we'll do a percent difference. All right. Now, the other objective for the day, in addition to measuring the specific heat, is we want to do some energy cost calculations. Yes, you actually have to do this. Okay, sometimes students go, we were just talking about energy costs. we didn't actually have to calculate anything. Yeah, you do. You have to go in and find out how much it costs to heat up the water. So what do you think? If we have some water here and we heat it up for 15 minutes and it goes from like 20 Celsius up to 35 or 40 Celsius, how much is that going to cost in terms of electrical energy? So let's take a look at the cost. Now, I went to my PG&E bill, and what I found for PG&E is for electricity, they don't use joules. Even though joules are standard units, they use these things called kilowatt hours, which, why aren't they just using joules? Anyway, so the kilowatt hour, 1 kilowatt hour of electricity is 21.775 cents. They're not kidding around with the significant figures. They've got that down to 5 significant figures, right? Now, a kilowatt hour would be, there's always the question, is that an energy unit? Or is that a power unit? And it's an energy unit, because it's a power multiplied by a time. So it's the equivalent of something that is 1 kilowatt, 1,000 watts, which would be 1,000 joules per second, and that operates for a full hour, which would be 3,600 seconds. So if I take 1,000, multiply it by 3,600 seconds, I get 3.6 million joules. So why don't they just use joules or megajoules? Why did they introduce other units? Anyway, we're just going to have to deal with that. Now, just for comparison, I wanted to find out what's the cost of natural gas compared with the electrical costs. So the natural gas energy is measured in therms. They didn't use joules here either. Why can't they just use standard units all the way through? Then we could do a very quick comparison between the two. Instead, we're going to have to step through some calculations here. So 1 therm is 121.724 cents. So again, they're being very specific about how much that energy costs in terms of natural gas. Now, if you guys have looked at your PG&E bills or looked at a PG&E bill, you'll know that they have different tiers. When you start using electricity for the month, they charge a certain amount. If you cross some kind of a threshold, they start charging you at a higher rate. Okay, and I actually had some solar panels. So solar panels are great. We had some solar panels put on our house a couple years ago, and since that time, we're generating enough electricity for the year that we don't have to pay for any electricity. In fact, currently we're overproducing. So at the end of the year, we actually get a refund from, in terms of our electrical use, from PG&E. They pay us back a certain amount, a certain portion of the excess electricity we've generated. They actually give us a stipend at the end of the year. And we're in the process of getting rid of our natural gas appliances because we've got to deal with global warming. And so we're trying to eliminate using fossil fuels, natural gas as an example. So we've gotten rid of our furnace. We got rid of a natural gas furnace and replaced it with a heat pump. That's right, a heat pump from thermodynamics, from what, chapter 19? 20? 20, chapter 20. So, so the heat pumps run completely electrically. And then we also got rid of our gas range, and we're in the process of switching over our gas clothes dryer. So eliminating these natural gas appliances and then switching over to electricity. And then you know what also we have to do is we've got to get all of our energy production coming from renewable energy sources. So our electric power plants, like half the energy generated in California is still coming from natural gas turbines. And so that, it doesn't really help if the natural gas is being used to generate the electricity. Anyway, getting back to the energy units here. So 1 therm is 100,000 British thermal units. I looked that up. And a British thermal unit is 1,056 joules. So a therm is the same thing as 105,600,000 joules. Why can't they just put it in joules right from the start? Anyway, I did a comparison. I ran some numbers. It turns out that based on these costs, electricity is 1 megajoule, a million joules of electricity from PG&E, costs 6.049 cents. Whereas natural gas, a megajoule of natural gas is 1.15. So you can see the incentive in terms of the cost of energy really favors natural gas currently. All right, so electricity actually, joule for joule, costs about 5 times as much. So again, more solar panels going up, for example, means that you don't have to worry about that a higher cost of electricity. Because once you get the solar panels in place, you're not paying for the electrical energy. You're generating it yourself with the solar panels. All right. So what we want to be able to do is find out what was the cost for today. So for that, I think the results table I want to work from. So I'll have notes on this. We'll have this in the slides. So what we're going to have is energy costs. So let's see, we're going to do 3 runs. 1, 2, 3, and then we're going to ask how much did it cost, electric cost, and then just for a comparison, find out how much it would have cost to use natural gas instead. So we'll do that for each of the 3 runs, the electric cost and the natural gas cost. Now how would I do that? What is it that we get charged for? And we get charged for the amount of energy. So I would say maybe work from these numbers right here. So this is saying for every million joules, it's 6.049 cents. For every 1 million joule of natural gas, 1.153. So those are the costs for those different energy sources. And what we can do to calculate how much energy did we use during one of the runs? Well, the energy is going to be equal to the power times time. So we've seen this formula. We saw this in mechanics too. We saw this in kind of classical physics, and then we saw it again we're seeing it again now in thermodynamics and with electrical energy. In any case, what we can do is find out how much power. Now the power, it's right here. So all I got to, right here, let's say. Let's take the VRMS, multiply it by the IRMS, the voltage times the current. That's going to give us the power. I just have to multiply this by the time. So how long are the runs? If the runs are 15 minutes or 20 minutes, that can be converted into seconds. And I can take that time multiplied by the power that we've calculated here. And that'll tell us how much electrical energy we used during that run. So calculate how much energy we used. You can put that in a table somewhere too, how much energy was used, and then calculate what the cost would be for the electricity we used, and then calculate how much the cost would be if we had used natural gas instead. All right, so let's do this. Let's get this set up on a table, and we'll get a closer view of some of this stuff. All right, so here's the setup. I've transferred this over to a table. Let's start over here with the power supply. Got the power supply plugged in. And here are the options that I had, so you can see there were a lot of different voltages that I could have plugged into. I went with this one up here, went with the 6.3 volts AC, 3 amps max is what it says. And then what I've got is, I can stand back a little bit here and see the wiring. So the red wires I've used for the main part of the circuit,
And those are going into, let me lift this out. Everything's turned off. There is the heating element, okay? That's down inside, so let me turn this to the side here. That's the heating element. That's the water that I've measured. It was, what, 170 something grams maybe? So I'm going to put that down inside. Now you can see the red wires are coming right up to that heating element. And so if I look at the circuit that we've got here, those black and red wires that we drew, those are the red ones that I've got here going into the heating element. And then I've connected right at the junction point where the posts are on the calorimeter, I've connected that to a voltmeter. All right, so what I'm going to do then is I'm going to turn this voltmeter on, and I'm going to select AC. So I got a voltmeter set to AC. Now this one, remember this is our ammeter, so it's plugged in a little differently. See the connections over here with the voltmeter, common and volts. This one is common and amps. I'm going to turn this one on too. It gives me a warning if I've done something dangerous, so I'm hoping we're okay. So there's the AC. So right now, this is reading 0, this is reading 0. I've double checked, and ooh, I got to get my thermometer back in there. So the thermometer's back in there. I've read the, well, I haven't read the starting temperature yet. So I'll do that in just a minute. Now you might be thinking, well, wait, don't I have to coordinate turning on the power supply with the reading the thermometer? And not necessarily. So what I could do is, let me turn this on. We're ready. This is the big moment. There we go. So the ammeter is fiddling around here now. It's reading like 2.5 amps right now. And the voltmeter is 6.68, something like that. So I've got the ammeter reading current, and I've got the voltmeter reading volts. And whenever I'm ready, I can start taking data. Now, I don't want the water to heat up too much before I start taking data. But, you know, I can get situated here and take a minute or so. And then whenever I'm ready, I can start my timer, and I can start taking data. All right, so I've been here for a few minutes now and starting to collect some data. Temperature is headed up. Thermometer looks good. I got some spare thermometers over here. The voltmeters and the ammeters look like they're pretty stable, so I think that's it. If you guys have questions on this, let me know. I plan to be here for another 20 minutes on each of these runs. So I've got probably 3 20-minute runs ahead of me. All right? Then we'll do some energy costs, and we'll see what the specific heat of water is. If you guys have any questions, stop by.